Welcome to lecture number 3 for ECE 341 Random Processes. In this lecture we look at enumeration. Now probability is defined as the number of times an event occurs as the number of trials goes to infinity. That leads to what we did the previous lecture, Monte Carlo experiments. Another way to figure out probabilities is enumeration. Here the idea is assuming all outcomes are equally likely, like on a 6-sided die, there's 6 outcomes, each is equally likely. What I can do is just count. How many outcomes are possible, how many of them are successes, and then the probability is exactly the number of ways an outcome happens divided by the total number of possible outcomes. So this is a brute force approach. In some cases it works really, really well. In other cases it's just too complicated. What we'll cover in this lecture is using enumeration to solve problems that we solved doing Monte Carlo, such as the probability of rolling a 1 on a 6-sided die, the probability of distribution of a max of d4 and a d6. Who's going to win a match? Player A rolls the d4 and a d6, means a 4-sided die, 6-sided die takes the maximum. Player B rolls a 6-sided die, B wins on ties. Who's going to win? I'll use the enumeration to find out the probability of A winning a 5-game match, the probability of rolling 6-sided dice, and drawing a full house or 3 of a kind in poker. So that's what we'll do with enumeration. So let's start out with the simplest case, a 6-sided die. Now the previous lecture we did a Monte Carlo simulation to find out the odds of rolling a 1 on a 6-sided die. And what you do is you write a Matlab script where I roll a 6-sided die and check to see if I rolled a 1. Once I can play the game one time, play it 1,000,000 times. And when I do that, I got these results. First trial, 166,219. Second trial, third trial. From that, I can tell you that the odds are about 0.166, give or take. That's one problem with the Monte Carlo simulation. You don't get exact answers. You can get a bound. When we get to student t-test, I can take this variability and tell you whatever the mean or average actually is, probability actually is, I can tell you what the maximum and minimum that probability will be. But I won't give you a specific number, won't give you an exact answer. A way to get an exact answer is the enumeration. With a 6-sided die, it's actually pretty easy. There are only 6 ways to roll a die. I can get the numbers 1 through 6. There is one way to get the number 1. You roll a 1. Hence the probability of a 1 on a 6-sided die is 1 divided by 6, 1/6. Now that we probably already knew. What's nice about this approach is it's a whole lot easier than rolling the dice 1,000,000 times, and the answer is exact. That's enumeration. Second case. Let's take a 4-sided die and a 6-sided die. Player A, what this means is, suppose I got a game where A rolls a 4-sided die, a 6-sided die, takes the larger of the two numbers. What's the probability A is going to score 1 point, 2 points, and so on? Well, I could do that with Monte Carlo. I could do that with enumeration. With enumeration, there's only 24 possibilities. The 4-sided dice can get the numbers 1 through 4. The 6-sided die get the numbers 1 through 6. Gives you 24 possibilities. Take the larger of the two, and that's the A score. So there's only one way to get 1 point. There are 3 ways to get 2 points. There are 5 ways to get 3 points. 7 ways to get 4 points. 4 ways to get 5 points. 4 ways to get 6 points. Therefore, the probability of getting each value is just the ratio. The probability of getting 1 point is 1 in 24, 2 points, 3 in 24, 5 in 24, and so on. What's neat about that is this is exact. And what I'm getting here is called the probability density function. It's the probability of getting each number. Now let's go back to what we did earlier. Roll a 4-sided die, or A rolls a 4-sided die, 6-sided die, takes the larger of the two numbers. B rolls a 6-sided die. What's the chance that A wins if B wins on ties? Now back with Monte Carlo, we got the odds being roughly 48.6%. Can I get the same answer using enumeration? Well, there's a problem here. There's just too many combinations. I've got a 4-sided die, a 6-sided die, 6-sided die. There's 144 numbers to go through, combinations. I don't really want to go through 144 combinations. I could do it, but that's kind of painful. Well, this is where a thing called conditional probability is kind of useful. The probability that A wins is, well, B is going to roll either the number 1, 2, 3, 4, 5, or 6. It's a little bit easier if I can guarantee if B rolled a 1, what's the chance that A is going to win? That I can compute fairly easily. But that only happens a sixth of the time. If B rolled a 2, what's the chance of A winning? Times probability of B rolling a 2. Likewise for 3, 4, 5, and 6. This is a conditional probability. I took a hard problem and split it into 6 easier problems. So, doing it that way, suppose B rolled a 1. If A wins on ties, A has to roll a 2 or higher. And from the previous results, going back over here, the numbers 2 on up, add up all these probabilities, that's the chance that A rolled 2 or higher. Then later we're going to do 3 or higher, 4 or higher, and so on. So we already have those odds. The probability that A is going to win, given that B rolled a 1, is 23 and 24. B's got a 1 in 6 chance of rolling a 1. If B rolled a 2, A has a 20 in 24 chance of winning. Has to roll 3 or higher. Chance that B rolled a 2 is 1 in 6. If B rolled a 3, is 15 in 24. If B rolled a 4, A has an 8 in 24 chance. 5, 4 in 24 chance. 6, A loses. B wins on ties. Okay, those are the conditional probabilities. I basically went back to the previous calculations and just added them up. Add these up. It's 23 and 24 chance that A got 2 or higher. 20 and 24, 3 or higher. 15 out of 24, 4 or higher, and so on. Put that all together, then the total probability that A is going to win is add up all the conditional probabilities. I get 0.486111. Now that matches up with what we did in Monte Carlo. Monte Carlo is about 48.6% of the time. With the enumeration, I can tell you exactly. These are the exact odds that A is going to win. A little more painful, but I also didn't have to run the simulation a million times. Let's do another example of enumeration. There is one type of enumeration called tree analysis. It's similar to an NBA basketball finals or baseball playoffs. Here, I've got two teams playing a match. Suppose A has a 60% chance of winning at any given match, and a match consists of 5 games. Whoever is the first to win 3 games wins the match. What's the probability A wins the match? Well, the previous lecture on Monte Carlo, we did that and got about 68% of the time A is going to win the match. Can I calculate the exact probability using enumeration? Well, one approach is called a tree diagram. If I start out at 0 games to 0, either A wins or B wins. If A wins, I'm now at 1-0. Either A wins or B wins. If A wins again, I'm at 2-0. If A wins again, I'm at 3-0. Kind of go through all these different paths. The probability of a win, that's in red, is 0.6. Probability of losing is in blue, that's 0.4. Now if we look at all these different approaches, there's one way for the match to end 3-0. There's 1, 2, 3, a bunch of ways the match could end 3-1, a bunch of ways could end 3-2, and that's all the ways that A can win. So counting. There's one outcome that's 3-0. The probability that A wins 3 times in a row is 3 wins for A, 0 wins for B. So that's 1 times P cubed. There's 3 ways the match ends 3-1. So that's 3 ways it ends. I've got 3 wins, P cubed, 1 loss times Q. Q is 1 minus P, 40%. There's 6 outcomes that are 3-2. So there's 6 outcomes where A won 3 times, P cubed, B won twice. 0.4 squared. Add it all up, I get 0.68256. Similar to what we had with Monte Carlo, but this number is exact. If a team has a 60% chance of winning any given game, the chance they'll win a baseball playoff or basketball playoff is 68.2% of the time. What's nice about this is that answer again is exact. And kind of a sidelight. There's a slight difference between two problems. Suppose I have a bowl of 5 marbles, or 3 marbles, 2 black, 1 red. I want to draw out the red marble. Similar like I've got 3 keys, I want to find out which key opens the lock. If I sample without replacement, what happens is there's 3 marbles in the bin, I pull one of them out. If it's the red marble, game's over. Key open the door. If it didn't open the door, either marble 2 or 3 are still in the bin. I'll then draw a marble, I drew 2, it's either 1 or 3 still left in the bin. I'll draw one at random, it'll be either 1 or 3. If it's 1, I found the right key, I got the red marble. If it was a 3, now the only marble left is the red one. So these are all the different ways I can draw a marble out of a bin of 3 marbles until I get the right one. That's sampling without replacement. When I sample a marble, I take it out, I remove it. Sampling with replacement is a much different problem. With replacement, I'll have 3 marbles. I pull one of them out at random. If it was red, I've got the right key, game's over. Otherwise, I put the marble back into the bin, shuffle them, draw again. I again have a 1 in 3 chance of getting the red marble. If I get the wrong one, I put it back, draw again. Again, I've got a 1 in 3 chance. This can go on to infinity, in theory. To handle the problem of sampling with replacement, I need a different tool. That tool is going to be a Markov chain. I can't really use enumeration with an infinite series. It can't go to infinity. But there are tools. Enumeration isn't one of them. So that's one way to do enumeration. Another way to do enumeration is brute force. That's Matlab. I'm going to grind through every possibility. And that's kind of what enumeration is. It is a no finesse, raw power, brute force approach to solve a problem. With Matlab, it's actually not a bad way to. So let's go back to the rolling the dice. 4-sided die, 6-sided die. A takes the maximum of the 2. B rolls a 6-sided die. So he wins. There's 144 different combinations. That is not a problem for Matlab. What I do in Matlab is I'm just going to go through every combination. The 4-sided die can take on the numbers 1 through 4 and do nested for loops. For each value of the first die, I can roll a 6-sided die. For each of those combinations, I can roll a third 6-sided die. Now when I do that, I've got all my possible die rolls. Here's the number of die rolls I'm doing. A is the maximum of D1 and D2. B is D3. If A is greater than B, then I win. Spin through every combination. If I run that, that took 0.00027 seconds, 271 microseconds. Not a challenge for Matlab. I ground through 144 different die rolls. 70 of them were successful. Therefore, the ratio is 70 over 144, 0.48641. 0.4861. That's enumeration with Matlab. Same answer I got with conditional probabilities, but actually a whole lot easier. Another example. Let's go back to Parkle. In the previous lecture, we looked at the probability of getting 2 triples or 1 triple in Parkle using Monte Carlo. When we did that, I got 2 triples 37 times out of a million rolls, 1 triple 308,000 out of a million rolls. So that's roughly the odds. 37 in a million, 308,000 in a million. Those are approximate. Can I calculate the exact odds using enumeration? Well, to do that, there's 46,656 ways to roll 66. That's just 6 to the 6th power. The first die can have the numbers 1 through 6, second die is the number 1 through 6, third die the number 1 through 6, and so on. So I've got to grind through 46,000 different combinations. Painful by hand, not a problem for Matlab. Kind of the way you do that is you put it in nested for loops. So here's the first die, can take on the numbers 1 through 6. For every one of those numbers, the second die can take on the numbers 1 through 6. Likewise, third, fourth, fifth, sixth. So this is every combination of 6 dice. And I can check. So here's the Matlab program. I'm going to go through every combination of 6 dice, count, run that. There are 46,656, which is 6 cubed, and that took all of 16 milliseconds to go through. Okay, now that I can go through every combination of dice, let's check to see what kind of die roll it is. I'm going to have a variable called f. That's the frequency of each number, the frequency of 1s, 2s, 3s, 4s, and 5s, and so on. So f of I is how many rolls were a 1, f of 2, how many rolls were a 2, f of 3, how many rolls were a 3. Sort in descending order. So for example, if the roll was 2, 5, 2, 2, 5, 6, when I'm done, f of 1 is 3. The highest frequency was 3 of a kind. The next highest frequency were the 5s. There were 2 5s. Next highest frequency is the 6. There's 1 6, and then everything else is 0. Okay, now that that works, I'll then check. Was the highest frequency 3 of a kind? Second highest frequency is also 3 of a kind. I've got 2 triples. If the highest frequency is 3 of a kind and the second highest frequency is not 3 of a kind, I've got 1 triple. So putting that all together, I've got this program. So I'm going to go through, got my 2 counters, 2 triples, 1 triple, number of rolls, go through every combination of die rolls, count, and then check. Count the frequency of each number, sort in descending order. If the highest frequency was a 3, and the second highest frequency is a 3, that's 2 triples. Highest frequency is a 3, second highest frequency is less than 3, that's 1 triple. Close all the for loops, then display the results. So I did that. That took 579 milliseconds, and I counted. There are exactly 300 ways to get 2 triples. There is exactly 14,400 ways to get 1 triple. And that seems like a tough way to do it, but again with MATLAB it's not that bad. I went through 47,000-ish combinations in all of 0.5 seconds. Try it again. What's nice thing about enumeration is I get the exact same answer every time. This is exact. Different than Monte Carlo. Monte Carlo, I got a different number every time I ran it. Enumeration, I always get the same answer. So that's an exact answer. So those are the results, meaning that there are, well, I think the ratio 300 over 46,000, that's the probability of getting 2 triples. 14,400 over 46,000, that's the probability of getting a single triple. Last case we're going to look at is poker. Let's find out what's the probability of getting a full house and 3 of a kind in poker. Now the first thing you need to do is you need to deal out a hand. So this is a little bit different than the dice. Back with dice, let's go back to here. I go through the numbers 1 through 6. Each of these starts at 1, ends at 6. For poker, it's a little bit different. I go, first card is anything from 1 to 52. The second card doesn't start from 1. If I did that, that would say I could in theory get 5 ace of spades. Once the ace of spades has been dealt, the second card cannot be the ace of spades. There's only one of them in the deck. So I've got to start at the first card plus 1 to the end. The next card, card 3, starts at the second card plus 1. So this is the ace of spades. I'll start with the 2 of spades, 3 of spades, 4 of spades, 5 of spades. have to increase the index. And technically, I want to end this earlier, but that'll work out at the end. If this is 52, I'll just skip these loops because I can't get to 53 and so on. Let's find out how many hands there are of poker. So I'll run this code. It takes a while. It goes through every possible poker hand. That took 2.7 seconds. There is 2,598,960 hands of poker. That's one way to calculate this. Next lecture, when we get to combinatorics, we'll look at can I calculate that number without having to do this brute force approach. Again, this is exact. Every time I run the code, I get the same answer. Once I deal out a hand, I've got to find out what kind of hand that is. We did this back with Monte Carlo. My hand is just those cards, -1. It works a little bit easier if I start from 0 rather than 1. The value of the card is the hand mod 13 plus 1. The suit is the floor of hands over 13 plus 1. So that way, 0 through 13 is value. Actually, 1 through 13 is value. 1 through 4 is the suit. For example, if I have the hand is 1, 7, 9, 22, 47, that's my counting. The value would be this number, mod 13 plus 1. So this is the 2. The suit is this one. This is the first card is the 2 of clubs. Card 0 is the ace of clubs. Card 7 is the 8 of clubs. Card 9 is the 10 of clubs. Card 22 is the 10 of diamonds. Card 47 is the 9 of spades, fourth suit. So there's my hand. Okay, once I go through every combination and I know what each hand is, what the value of each card is, what the suits are, I can check for different things, like straights, flushes, 3 of a kind, and so on. Let's just look for full house and 3 of a kind. To do that, I want to look at the card's frequency. So here's the frequency of 13. Aces, 2s, 3s. So f of 1 is the frequency of aces, f of 2, the frequency of 2s, f of 3, frequencies of 3s, and so on. Sort in descending order, f of 1 is the card with the highest frequency. If the highest frequency is 3, I've got a 3 of a kind. If the second highest frequency is 2, I've got full house. If the highest frequency is 1 and the second highest frequency is less than 2, I've got 3 of a kind. And there's other types of hands too. There's 4 of a kind, straight flush, royal flush, straight, flush, so on. I'm just looking for these two. We'll worry about the other cards later. So this is the resulting code. I'm going to go through every hand for that hand, calculate the values, the suits, calculate the frequencies, sort in descending order, and check. Is it a full house? Is it 3 of a kind? And then close up all the 4 loops. So if I try that, this is kind of challenging the computer. If I let this go, I'm displaying the first card, second card. So I'm going through the ace of clubs is the first card. Now looking at the first card is the 2 of clubs, 3 of clubs. This takes a while to run. It's going to stop when C1 gets to 52. So this is a problem with enumeration. It does work. It can take a long time. But once you get the answer will be exact. For example, if I want to know poker hands, I want to know the exact odds of getting certain values. Well, this will do it. It's going to take some time, but the answer is exact. And it's actually not all that bad. It's speeding up. The reason it's speeding up is when this is 1, I've got to go through 52 combinations. Eventually it speeds up at the end. When I'm done, this is how many different ways I can get a full house. This is how many different ways I can get 3 of a kind. And that took 54 seconds. And those numbers are exact. That's the beauty of enumeration. You get exact answers. The problem, you can kind of see what's going on. The problem is it takes a long time sometimes. For example, for poker, this was 186 seconds on one computer. On the computer in my office, I'm making these videos. This is a newer, better computer. Only took 54 seconds, but that took a while. That's with a 5-card hand. There's some versions of poker where you are dealt 7 cards. Of those 7 cards, make the best poker hand. Well, kind of figure how long that's going to take. The next 2 cards, those going to be at least 52 times longer. 50 times 50, that's a lot of time. That can take hours. For such a thing, I might need a better tool. There are better tools out there. Those better tools are things like combinatorics, our next lecture. But you don't have to use anything fancy. You can use raw power, brute force. That's enumeration. And I can check my answer. In this case, poker is pretty well analyzed. I can go to Wikipedia. And Wikipedia will tell me the number of hands that are full house, number of hands that are 3 of a kind, and surprise, surprise, that matches exactly with what we did with enumeration. Basically, poker's been analyzed to death, so the odds of different hands are pretty well known. And this is one way to get those answers, enumeration. So, kind of in summary, Monte Carlo simulations, they do work. If you can play a game one time, I can throw in a for loop and play it 1,000,000 times and get an idea what the probabilities are. Problem with Monte Carlo is it doesn't give you exact numbers. It'll give you a ballpark, but not exact. When we get to a t-test, later on at the end of the semester, I can bracket the probability. Tell you, I don't know what the probability is, but it's somewhere between these 2 bounds. That's Monte Carlo. With enumeration, I get exact answers. I can simply count. How many different ways can you deal out a poker hand? How many different ways can you roll 6 dice? And I count. How many of them were successes? How many of them were 2 triples? How many of them were full house? How many were 3 of a kinds? Then the probability is just the ratio. How many successes are there? How many different outcomes are there? That ratio is the exact probability of that outcome. Sometimes enumeration works really, really well. For example, if a 6-sided die, probability of getting a 1 is 1 in 6. That's enumeration. Sometimes it works okay. With Matlab, I can count, go through every combination of 6 6-sided dice. I can actually go through every poker hand, but that's kind of pushing it. Sometimes it's just not feasible. If I were to deal 7 cards in poker rather than 5, that's going to take roughly 2,000 times longer. That's going to take several days. For that case, I need a better tool. That better tool is called combinatorics. That's what we'll be covering in our next lecture. So that's lecture number 3 for ECE 341 Random Processes, Enumeration.